As the world becomes more aware of climate change and its serious consequences, many countries and industries are looking for better ways to reduce carbon emissions and energy use. One major solution that has gained attention is hydrogen energy. It's a clean energy option that can be made using a variety of other energy sources, making it a renewable and flexible choice. However, in order for hydrogen energy to become more widely used, it's essential to find reliable and efficient ways to store hydrogen. There are three main ways to store hydrogen: as a gas under high pressure, as a liquid at very low temperatures, and in solid materials. Among these, storing hydrogen in solid materials known as solid-state hydrogen storage has several clear benefits. It can hold more hydrogen in a smaller space, it works under lower pressure, and it's generally safer than the other methods. These features make it a strong option for building a dependable hydrogen storage system. Solid-state hydrogen storage depends on special materials called carrier materials. These include metal hydrides, complex hydrides, and carbon-based materials. What they all have in common is their ability to absorb and store hydrogen. They do this either by physically attracting hydrogen molecules to their surface, a process called physisorption, or by chemically bonding with hydrogen called chemisorption. These processes allow the hydrogen to be safely stored and then released when it is needed for use. A typical utility company looking to use hydrogen as part of its clean energy strategy would be especially interested in solid-state storage. That's because of the safety, compactness, and ease of use that these materials can provide. Solid-state storage doesn't require extremely high pressures or ultra-low temperatures, which makes the overall system simpler and potentially less expensive. There are many different types of solid-state hydrogen storage materials available today. Each one has its own strengths and weaknesses depending on its physical and chemical properties. These include how much hydrogen the material can store, how easily it can absorb and release hydrogen, how it behaves under different temperatures, and what it's made of at the microscopic level. To understand these materials better, researchers and engineers study their thermodynamic behavior, how they are made, and how they perform in real-world conditions. Let's talk about one of the ways hydrogen can be stored through a process called physisorption. This method works by attracting hydrogen gas molecules to the surface of a solid material using very weak forces, known as van der Waals forces. These forces don't involve any chemical reactions. Instead, they are more like gentle attractions that happen when molecules get close to each other. Think of it as hydrogen gently settling onto the surface of a material without bonding too deeply. In this process, the hydrogen molecules don't split apart or change form. They stay as complete hydrogen molecules and simply gather on the surface of the material. This attraction depends on a property called polarizability, which tells us how easily a hydrogen molecule's electrons can shift around. Materials that have high polarizability tend to attract hydrogen more strongly, which helps improve storage. The strength of this attraction, called the interaction energy, is usually pretty low, around 4 to 5 kilojoules per mole. This tells us that hydrogen is only lightly held in place. Because this type of bonding is so weak, it's easier to store and release hydrogen under normal conditions, but it also means that storage isn't extremely dense or compact. To hold a decent amount of hydrogen using this method, we need materials with lots of surface area. The more surface there is, the more room there is for hydrogen to gather. For example, 1 mole of hydrogen needs at least about 86 square meters of surface area to be stored effectively. Materials like graphene, which is a single layer of carbon atoms, are ideal because they offer a very high surface area, over 1,300 square meters per mole. Because of this, graphite-based materials can store up to 3% of their weight in hydrogen. If you want to calculate how much hydrogen a material can theoretically store, there's a simple formula. Just multiply the material's specific surface area SSA by a constant value to 0.27 times 10. This gives you the hydrogen storage capacity as a percentage of the material's weight. Now let's look at another way hydrogen can be stored: chemisorption. Unlike physisorption, which involves weak forces, chemisorption is a much stronger process. This method happens when hydrogen molecules form actual chemical bonds with the surface of a solid material. That means there is a real exchange or sharing of electrons between the hydrogen and the surface atoms. When this kind of bond forms, it's more like a permanent attachment, similar to how atoms combine to make molecules. Because these are strong chemical bonds, chemisorption usually can't be easily reversed. Once hydrogen is stuck to the surface, it takes more energy to remove it compared to physisorption. That's why materials using chemisorption are often better for long-term or stable storage of hydrogen, especially in systems where safety and control are important. In simple terms, the surface of a solid material acts like a host that chemically grabs onto hydrogen atoms or molecules. This stronger connection means the hydrogen is held more tightly, making it less likely to escape accidentally. While this makes chemisorption very useful in many storage applications, it also means it's harder to release the hydrogen when you need it, unless specific conditions are met, like higher temperatures. It's also important to understand that chemisorption and physisorption aren't completely separate. In some materials, both processes can happen at the same time or in sequence. For example, hydrogen might first get loosely attached to a surface through physisorption, and then it might go on to form a stronger bond through chemisorption. When it comes to storing hydrogen in solid materials, carbon-based materials have gained a lot of attention. These materials are part of a wider group that includes things like porous inorganic substances, metal organic frameworks (MOFs), covalent organic frameworks (COFs), metal hydrides, and chemical hydrides. But among all of these, carbon-based materials stand out for a few very practical reasons that make them especially useful for hydrogen storage. One of the biggest advantages of carbon-based materials is how well they can absorb hydrogen. They're known for having a very porous structure that means they have tons of tiny spaces inside, almost like a sponge. This gives them a large surface area, which is extremely important because hydrogen tends to stick better to materials with more surface to attach to. The larger the surface area, the more hydrogen these materials can store. Another reason these materials are attractive is because they're very lightweight. That makes them especially useful in industries where weight matters, like in transportation or portable energy storage systems. A lighter storage system means better energy efficiency and easier handling. Carbon-based materials are also known for being easy to use over and over again. They allow hydrogen to be released or desorbed without much difficulty. This ability to store and then release hydrogen efficiently and to repeat that process many times makes them cost-effective and environmentally friendly over the long term. Carbon-based materials are one of the most widely explored options when it comes to storing hydrogen, and the way they work is both simple and effective. The main process behind their hydrogen storage ability is called physisorption. This means hydrogen gas sticks to the surface of the carbon material through weak forces, not chemical bonds. These forces are strong enough to hold the hydrogen in place, but weak enough that the hydrogen can be released later when needed. This makes physisorption a good fit for systems that need to both store and release hydrogen efficiently. In real-world use, carbon materials usually absorb hydrogen at lower temperatures and higher pressures. This makes it easier for the hydrogen to settle onto the surface of the material. Later, when the temperature is increased, the hydrogen can be released again. This cycle of absorbing and releasing hydrogen makes carbon-based materials especially attractive for reusable storage systems. A typical utility company considering a shift toward cleaner fuels could benefit from this technology because it is relatively easy to control and doesn't require extreme conditions. Graphite is one example of a carbon-based material that has been closely studied. Scientists have looked into how hydrogen interacts with graphite using advanced tools and techniques. While it is technically possible for hydrogen atoms to form chemical bonds with graphite, a process called chemisorption, this doesn't happen easily. The reason is that there is a high energy barrier that must be overcome for the chemical bond to form. This makes chemisorption rare in carbon materials like graphite, especially under normal conditions like room temperature. Because of this, most hydrogen storage in carbon-based materials happens through physisorption, not chemisorption. This is good news for systems that need hydrogen to be stored safely, but also released easily when required. There are many different forms of carbon materials used for this purpose, including activated carbon, graphite fibers, carbon nanofibers, and carbon nanotubes. Each type has its own structure and surface area, which can influence how much hydrogen it can hold and how well it performs in different applications. Activated carbon is a type of carbon material that comes in different forms, such as powder, granules, or small columns. What makes it special is its very porous structure, meaning it has a lot of tiny holes and spaces inside. These pores give activated carbon a very large surface area, which is important for storing gases like hydrogen. When it comes to hydrogen storage, activated carbon works based on a process called supercritical gas adsorption. This simply means that hydrogen gas sticks to the surface of the carbon when it is under high pressure and low temperature conditions. The more surface area and better pore structure the carbon has, the more hydrogen it can store, especially at low temperatures. To make activated carbon that is good for hydrogen storage, manufacturers usually use one of two main methods: chemical activation or a mix of chemical and physical activation. These techniques are designed to create activated carbon with an extremely high surface area. In the chemical activation method, the type of material used to make the carbon, called the raw material, can vary. The raw material is treated with chemical agents that help form the pores and increase the surface area. Some common chemical agents include alkali metals, certain hydroxides, inorganic salts, and acids. Out of all of these, potassium hydroxide (CO) is known to be the most effective. It helps produce activated carbon that performs very well in terms of gas storage. One study explored how high-sulfur coke could be used as a raw material, with KOH as the chemical agent. The result was a series of activated carbons with extremely high surface areas, some reaching up to nearly 4,000 square meters per gram. The researchers then tested how well these materials could store hydrogen. They found that temperature played a big role in performance. At very low temperatures, around 93 K, which is colder than liquid nitrogen, the material could store up to 9.8% of its weight in hydrogen under pressure. But at room temperature, around 293 K, the storage dropped significantly to 1.9% under similar pressure. When making activated carbon for storing gases like hydrogen, the way it's prepared has a big impact on how well it performs. One popular method to improve the quality of activated carbon is called the combined chemical-physical activation method. This process blends two steps. First, chemical treatment to help develop the pore structure, followed by a physical step that further refines the carbon-using gases. In the chemical part of the process, several things need to be carefully managed. These include the amount of chemical activator that is added, how hot the process gets, how long the activation lasts, and the type of raw material being used. All of these details can change how the final activated carbon turns out. The goal is to create a material that has lots of tiny pores, which increases the total surface area. More surface area means better ability to hold hydrogen. However, it is important to avoid making pores that are too big, called mesopores and macropores, because those are not as helpful for hydrogen storage. By keeping the pores mostly small, the carbon becomes better at capturing and holding gas molecules. Once the chemical activation is done, the next step is physical activation. This is sometimes called gas activation. In this part, certain gases like carbon dioxide, steam, air, nitrogen, or oxygen are passed over the carbon material while it's heated. These gases help clean and open up the pore structure even more, removing parts of the carbon that aren't useful and improving the overall quality of the final product. This two-step method using both chemical and physical activation allows for more control over the final structure of the carbon. It results in a material that has a high surface area, the right kind of pores, and strong performance in storing hydrogen. Because of this, it is often a method that researchers and even a typical utility company might explore when looking for advanced materials that can support clean energy storage solutions. When we look at how hydrogen gas interacts with activated carbon, one important concept is something called an adsorption isotherm. This simply means a way to describe how much hydrogen gets stored on the surface of the activated carbon at different pressures and temperatures. Scientists have studied a special kind of activated carbon that has an extremely large surface area, about 3,886 square meters for every gram of the material. That's a huge amount of surface for hydrogen to stick to. What they found is that this kind of carbon follows what is known as a type I adsorption pattern. In simple terms, this means that the carbon grabs onto hydrogen quickly and strongly when the pressure starts to increase, especially in the lower pressure range from 0 to 6 megapascals MPa. At lower temperatures, this process works even better. Cold conditions make the hydrogen stick more easily to the carbon's surface. As the pressure goes up, especially in the higher pressure range, the surface area of the activated carbon becomes even more important. The more surface area the carbon has, the more hydrogen it can hold. That is why having a well-designed pore structure and a very large surface area is critical in making activated carbon a good option for hydrogen storage. Another great thing about this material is that hydrogen doesn't just stick well, it also comes off quickly when needed. This fast on and off behavior is important for practical use, like in vehicles or energy systems where hydrogen needs to be added and removed efficiently. In testing, the results showed that the amount of hydrogen stored changed a lot depending on temperature. At room temperature, about 293 K, at pressure of 5 megapascals, the material could store 1.9% of its weight in hydrogen. But at a much colder temperature of around 93 K and a slightly higher pressure of 6 MPa, the storage jumped to 9.8%. That's a big improvement, showing that lower temperatures really help boost performance. When hydrogen gas is stored on activated carbon, it sticks to the surface of the material, a process known as adsorption. But this sticking process isn't just about surface area and pressure, it also involves heat. The energy involved when hydrogen molecules attach to the carbon surface is called the heat of adsorption. To put it simply, the heat of adsorption tells us how much energy is either released or absorbed during this process. Scientists sometimes call this value the equivalent heat of adsorption. It is a way to measure how strong the bond is between the hydrogen and the carbon surface. This value can be found using an equation known as the Clausius-Clapeyron equation. While the equation itself is technical, what matters is that it helps us understand how temperature and pressure affect hydrogen storage. Here is how it works. By collecting data on how much hydrogen gets adsorbed at different temperatures and pressures, researchers can plot a graph. This graph helps them draw straight lines that represent how the gas behaves under various conditions. The slope, or steepness, of those lines tells us the heat of adsorption value. From research, it was found that this heat of adsorption value for hydrogen on superactivated carbon is actually quite small. Most of the values fall within a narrow range between 4.8 and 6.5 kilojoules per mole. What does this mean in practical terms? It means that hydrogen doesn't need a lot of energy to stick to or come off the carbon surface. This is actually a good thing because it allows for faster and easier storage and release of hydrogen, which is important for real-world energy applications. Graphite nanofibers, or GNFs, are tiny fiber-like materials made up of many stacked layers of graphite flakes. Unlike carbon nanotubes, GNFs don't usually have a hollow center. They are created through a process called pyrolysis, which means breaking down gases like olefin, hydrogen, and carbon monoxide using high heat. This reaction takes place on the surface of a special metal catalyst, typically at temperatures between 700 and 900 Kelvin. The result is a nanofiber made of closely packed layers of graphite that are only 30 to 50 nanometers wide, with the layers spaced about 0.34 nanometers apart. Depending on how the layers are arranged and whether or not the structure has a hollow center, GNFs can be grouped into four types: flat, herringbone, tubular, and cup-like. Among these, the herringbone type has shown the best ability to store hydrogen. In earlier experiments, researchers produced flat, herringbone, and tubular GNFs and tested their hydrogen storage capabilities. The results showed that herringbone GNFs performed the best, storing up to 67% of their weight in hydrogen at room temperature and high pressure. Flat GNFs stored 53%, while tubular ones stored only about 11%. However, not everyone agrees with these numbers, since reproducing the same results has been difficult in later experiments. In general, the hydrogen storage performance of GNFs can vary a lot depending on how the materials are made and tested. Reports have shown hydrogen storage values ranging from as low as 1% to as high as 15%. These differences often depend on the specific experimental methods, the way the GNFs were prepared, and the testing conditions. One way to improve GNFs is by adding tiny particles of platinum PT to their surface. In one study, researchers used a chemical process to attach platinum nanoparticles to the surface of porous GNFs and then tested how this affected hydrogen storage. They found that adding platinum helped improve storage up to a point. When the platinum content reached about 3.4% of the total weight, the GNFs stored more hydrogen. But when more platinum was added beyond that, the storage capacity started to drop. This suggests that there is an optimal amount of metal that helps the material work better, and going beyond that can actually reduce its performance. Carbon nanofibers, or CNFs, are tiny fibers made up of many layers of twisted graphite flakes. These fibers are very small, typically between 10 and 500 nanometers wide and anywhere from half a micron up to 100 microns long. To give you a sense of scale, they are much thinner than a human hair, but longer than many other nanomaterials. CNFs sit somewhere between carbon nanotubes and regular carbon fibers in terms of size and structure. Because of their unique shape and structure, they are considered one-dimensional carbon materials. There are several ways to make carbon nanofibers, but one of the most common and effective methods is called chemical vapor deposition, or CVD. This method uses heat to break down hydrocarbon gases on the surface of a metal catalyst, which causes carbon atoms to build up and form the nanofibers. The temperature for this process usually ranges from about 500 degrees Celsius to 10 degrees Celsius. In one example, a mixture of nickel and silicon dioxide was used as the catalyst to grow the carbon fibers. After making the carbon nanofibers, researchers loaded them with a hydrogen-rich material called sodium alunate sulfur to improve their ability to store hydrogen. The hydrogen storage performance of these loaded CNFs was tested using a technique that measures how much hydrogen is released when the material is heated. At around 300 degrees Celsius, the carbon nanofibers released about 4.8% of their weight in hydrogen. This shows that CNFs have promising potential for hydrogen storage applications. One interesting way to make carbon nanofibers is through a technique called the electrospinning method. This process starts with a solution or melted form of a polymer, a kind of plastic-like material. The solution is sprayed and stretched by applying a strong electrical force, which pulls the fibers very thin. As the solvent in the solution evaporates, what's left behind are extremely fine fibers called nanofibers. These nanofibers are very tiny, much thinner than a human hair, and have unique properties that make them useful for storing hydrogen. In a specific example of this method, researchers used a special type of polymer called PAN, combined with tiny amounts of palladium salts. They used a version of electrospinning called coaxial electrospinning, which allows the creation of fibers with a core and outer layer. After making these fibers, they heated them to very high temperatures around 800 degrees Celsius in a gas mixture to turn them into porous carbon nanofibers. Tests showed that these fibers had tiny pores and special surface chemistry that helped them store hydrogen. When tested, the fibers could absorb and release hydrogen up to 0.35% of their weight at room temperature and normal pressure. Although this number may seem small, it's a step toward creating better materials for hydrogen storage. Another way to make carbon nanofibers is through the solid phase synthesis method. Unlike electrospinning, this method uses solid carbon materials as the starting point. These solid carbon sources are processed to create nanofibers without going through the liquid or gas phases. This approach offers a different way to control the structure and properties of the carbon fibers. When it comes to storing hydrogen in carbon nanofibers C and Fs, two important features make a big difference: the specific surface area SSA and the volume of micropores within the material. The specific surface area is basically how much surface is available for hydrogen to stick to, measured in terms of area per gram of material. Micropores are tiny, very small pores that can trap hydrogen molecules inside the fibers. Researchers studied how these two factors affect hydrogen storage by looking at C and Fs treated in different ways. They found that the relationship between the surface area and the amount of hydrogen the C and Fs can hold is quite straightforward. As the surface area increases, the hydrogen storage capacity increases in a straight line fashion. This means the more surface area the fibers have, the better they can store hydrogen. This effect becomes even stronger when the hydrogen is under higher pressure, making surface area an especially important factor for practical storage. The relationship between micropore volume and hydrogen storage is a bit different. It follows a curve instead of a straight line. When the micropore volume is small, increasing it causes a rapid increase in hydrogen storage. But as the micropore volume gets larger, the rate of increase slows down. This means that having more micropores is very helpful up to a point, especially under high-pressure conditions, where their impact on hydrogen storage is more noticeable. Carbon nanotubes, or CNTs, are tiny cylindrical tubes made from layers of graphene, which is a single layer of carbon atoms arranged in a hexagonal pattern. You can think of them as very thin hollow tubes that look a bit like rolled-up sheets of chicken wire or barbed wire. Their diameters are incredibly small, ranging from just a few nanometers up to several tens of nanometers. What makes CNTs special is their shape and size, which give them unique physical and chemical properties. There are two main types of carbon nanotubes: single-walled CNTs SWCNTs and multi-walled CNTs MWCNTs. The difference between them is how many layers of graphene make up the tube walls. Single-walled CNTs have just one graphene layer rolled into a tube, while multi-walled CNTs have several concentric graphene tubes nested inside each other. To create CNTs, scientists need to break down carbon sources into individual atoms or ions and then help those atoms arrange themselves into these tube-like structures. There are a few popular methods used for this. One common method is the electric arc process, where electricity generates an arc between carbon electrodes, vaporizing the carbon into nanotubes. Another way is laser evaporation, where a powerful laser is used to break down carbon targets. These methods can produce high-quality CNTs that are very straight and well-ordered, but they usually have a low yield and contain impurities like bits of graphite or other carbon particles. To clean these impurities, treatments using acids or alkalis are applied. Other common methods include catalytic cracking and chemical vapor deposition (CVD). In these approaches, gases containing carbon, such as methane or carbon monoxide, are broken down at high temperatures using metal catalysts, often made from transition metals. The carbon atoms then attach to the catalyst particles and form nanotubes. These methods can produce larger amounts of CNTs with better control over their size and structure. Researchers have also developed specialized techniques like the hydrogen arc method, which helps produce large quantities of very pure single-walled CNTs. Studies have shown that after some pretreatments like acid cleaning and heating, these SWCNTs can store hydrogen at levels between 4.2 and 4.7% of their weight. This is impressive because it is about 2 to 3 times better than the hydrogen storage capacity of some metal hydride materials. Carbon nanotubes, or CNTs, are known as some of the best materials for storing hydrogen. This is because they have a very large surface area and contain tiny pores called micropores, both of which help in holding hydrogen molecules effectively. Researchers have studied the hydrogen storage capacity of single-walled CNTs as WCNTs made by a special method called the hydrogen arc technique. When high-purity hydrogen gas at moderate pressure was introduced, these SWCNTs showed an initial storage capacity of about 4.2% by weight at room temperature. Since the tested sample contained only about half CNTs by weight, it is estimated that pure SWCNTs could potentially store as much as 8% hydrogen by weight, which is quite impressive. Computer simulations also support these findings. Studies have shown that SWCNTs with certain sizes, specifically around 1.17 nanometers in diameter with thin walls, perform best in storing hydrogen under normal temperature and pressure conditions. This means that not only the size, but also the wall thickness and internal structure of CNTs play an important role in how much hydrogen they can hold. Besides the physical structure, improving the surface of CNTs is key to increasing their hydrogen storage capacity even further. Scientists have experimented with different surface treatments to activate or change the CNT's surface properties. For example, one method involved grinding the CNTs and soaking them in strong acids or boiling them, while another method used heating in alkaline solutions followed by acid treatments. These processes help increase the surface area and make the surface more active, which allows CNTs to absorb more hydrogen up to about 5% by weight in some cases. Another technique to improve CNTs for hydrogen storage is ball milling, which is basically grinding the CNTs for different lengths of time. This mechanical treatment can initially increase the surface area and activity, making the nanotubes better at holding hydrogen. However, if ball milling goes on too long, the storage capacity may actually decrease. For example, after about 12 hours of ball milling, multi-walled CNTs and WCNTs showed a rise in hydrogen storage from 1.6% to 2.55% by weight. This shows that ball milling is a useful way to improve hydrogen storage, but needs to be carefully controlled. Metal hydrides are materials that can store hydrogen by chemically combining with it under certain temperature and pressure conditions. These materials are made of special metal alloys that react with hydrogen to form metal-hydrogen compounds. This process is reversible, which means the hydrogen can be absorbed into the metal or released back when needed, depending on the temperature and pressure. These hydrogen storage alloys usually consist of 2 kinds of metals. The first kind, called the element, includes metals like magnesium, titanium, vanadium, lanthanum, and zirconium. These metals help control how much hydrogen the alloy can store because they have a strong attraction to hydrogen. The second kind, called the B element, includes metals such as chromium, manganese, iron, cobalt, nickel, copper, zinc, and aluminum. These metals play an important role in how easily the hydrogen can be absorbed and released, and they also help control the heat involved in storing and releasing hydrogen. The process of storing hydrogen in metal hydrides happens in 3 main stages. First, when the metal alloy is exposed to hydrogen at a certain temperature and pressure, hydrogen atoms dissolve into the metal to form a solid solution without changing the metal's structure. This means the hydrogen mixes in small amounts, creating what is called the alpha phase. Next, as more hydrogen is absorbed, the metal alloy undergoes a change in its structure known as a phase transition. This change allows the metal to hold much more hydrogen, forming a metal hydride compound called the beta phase. At this stage, the metal is chemically combined with hydrogen. Finally, when the hydrogen pressure increases further, the amount of hydrogen in the metal hydride increases slightly, but the metal can keep absorbing and releasing hydrogen repeatedly without breaking down. During this whole process, when the metal absorbs hydrogen, heat is released, and when hydrogen is released, the metal absorbs heat. The way metal hydrides absorb and release hydrogen depends a lot on the temperature, pressure, and the type of alloy used. To understand how well these materials store hydrogen, scientists use something called the pressure composition temperature (PCT) curve. This curve shows key details like how much hydrogen the material can hold and how it behaves when hydrogen goes in and out. The PCT curve has different parts. One part shows when a small amount of hydrogen starts mixing with the metal called the alpha phase. Then there is a flat section called the plateau, where the material absorbs hydrogen without much change in pressure. This plateau represents the effective storage part. After this, the material changes completely into the beta phase, meaning it holds more hydrogen. When the temperature goes up, the plateau gets shorter. This means higher temperatures make it harder for the material to absorb hydrogen effectively. Scientists use an equation called the Van 't Hoff equation to calculate important energy changes during hydrogen storage. This helps understand how stable the metal hydrides are when they store hydrogen. The stability mostly depends on the enthalpy, or heat involved in the reaction. More negative enthalpy means the material is more stable. For good hydrogen storage at normal room temperature and pressure, the enthalpy should be between 30 and 40 kilojoules per mole. Complex hydrides are a special type of hydrogen storage material that is quite different from regular metal hydrides because they are salts. In these materials, hydrogen atoms are bonded tightly to a central atom inside the complex ion through covalent bonds. This complex ion then connects with metal ions using ionic bonds to form the full hydride compound. Typically, the chemical makeup of complex hydrides includes elements from the first or second groups of the periodic table, combined with elements like boron, aluminum, or nitrogen. One important feature of complex hydrides is that they can store a lot of hydrogen by weight anywhere from about 5.5% to as high as 21%. Hydrogen can be released from these compounds either by reacting with water hydrolysis or by heating them up pyrolysis. Complex hydrides come in three main types based on the chemical groups attached to them. The first type includes hydrides that contain aluminum hydrogen groups, such as lithium aluminum hydride and sodium aluminum hydride. The second type contains metal amides with nitrogen hydrogen groups, like magnesium amide or lithium amide. The third type involves boron hydrogen groups and includes substances such as lithium borohydride and magnesium borohydride. Each type has different properties, but all are useful for storing hydrogen efficiently. Aluminum hydride, specifically sodium alanate NaL4, is a material studied for hydrogen storage. When NaL4 breaks down, it does so into main steps. The first step happens at temperatures around 185 to 230 degrees Celsius and releases about 3.7% hydrogen by weight. The second step occurs at a higher temperature of about 260 degrees Celsius, releasing another 1.9% hydrogen. Altogether, NaL4 can release roughly 5.6% hydrogen. However, sodium hydride Na, a product of the breakdown, doesn't decompose until much higher temperatures above 425 degrees Celsius, which makes it less useful for practical hydrogen storage. Another important group of materials for hydrogen storage is borohydrides, with sodium borohydride NaB4 being the most studied. There are two main industrial ways to make NaB4. The Schlesinger method uses sodium hydride, trimethyl borate, and other chemicals to produce NAV4. The Bayer method uses sodium, boron oxide, silica, and hydrogen to create NABH4. Both processes are designed to produce this compound on a large scale. NAV4 releases hydrogen when it reacts with water, producing hydrogen gas, sodium metaborate, and water. Although NAV4 has a high theoretical hydrogen capacity, in real situations, it releases hydrogen more slowly and requires extra energy to start the reaction. To improve this, scientists add catalysts or use ball milling to speed up the process. One challenge with NAV4 is that its reaction can create borate waste and needs an alkaline environment, which may cause corrosion in storage and transport equipment. Despite these challenges, NAV4 is promising for hydrogen storage and fuel cells because it holds a lot of hydrogen and its reaction can be controlled easily.